Last class we looked at semiconductor process yield. Yield was essentially defined as the total number of wafers that come out divided by the total number of wafers that went in. The number of wafers that went in are of course the blank wafers, and the wafers that come out are the finished or the processed wafers. We saw that there were three main kinds of yield. One was the wafer fabrication yield or fab yield. The next was the sort yield, which related to the number of good or functioning dies in a given wafer, and then finally you had your packaging yield. The overall yield is related to the product of all three of the individual yields. We also saw something about the total cost of manufacturing of a semiconductor, and we found that yield is one of the important parameters that affects the variable cost of manufacturing. Lower the yield, which means lower the number of good chips or good dies, then higher is the cost of an individual chip. So today we are going to look at how the clean room design and contamination control is done in order to maximize the yield and minimize the cost. So one of the most important factors that affects the yield in a fab is the wafer contamination, which is why we essentially go for a clean room. Now this is especially important because we see that device dimensions are essentially shrinking. So when the first ICs were introduced in the late 1960s, a typical device dimension was of the order of micrometers or even hundreds of nanometers. But now we have devices that are only a few nanometers across, so that even contamination of the order of nanometers can essentially affect the device. So in such cases, the design of the clean room and minimizing contamination in it is critical in order to make sure we have good functioning devices and to also increase the yield. So when we look at clean room contamination, contaminants can be divided into 5 main categories. So the first one is particles, then we have metal ions, and we will see the role of each of them briefly. Then we have chemicals, so the process chemicals that are used, bacteria, and then finally something called airborne molecular contaminants or AMCs. These are essentially the 5 main categories under which contaminants are classified, and all of this has a potential for affecting the device performance. So let us first look at particles. So we saw that in the case of semiconductors, we have device dimensions that are of the order of nanometers. So we can compare that to the size of a typical dust particle, For example, if you have a dust particle, a typical size is approximately 1 micrometers. So already a dust is more than 100 times larger than the size of the device. If you look at the size of the human hair, if you look at the diameter, this is approximately 100 micrometers, which is 10 to the 5 times bigger. So the idea being that even small dust particles have essentially sizes that are much larger than the device dimensions. So any of these contaminants can essentially affect a device. So what are some of the sources of particles in the case of a fab? So the main source of particles is the people who actually work in the fab. So these are the workers. This is one of the reasons that special suits are worn by people working in the fab in order to minimize any particle sources. You can also have particles that are generated by the equipment. So most process equipment essentially have metallic components. So even a small thing like a metal screw that is rubbing against another surface can generate metal particles, and these particles again will be of a size usually of a few microns, which can again affect your device. You could also have processing chemicals contributing particles. For example, if a chemical has some sort of impurity or some sort of dust, so this again can deposit onto the wafer and again contaminate the wafer. This is one of the reasons why defect measurement in the case of a fab is really important. Using defect measurement, we can track down the density of the defects and also the size, shape and chemical composition of the defect. So this in turn will be used in order to find out the source of the defect. So for example, if you have a metallic defect in the case of wafers, then one particular source of the metallic defect can be the process equipment. So this is something that can be used in order to troubleshoot the equipment and to remove the source of the defect. So generally when we look in the case of semiconductors, we said that the device dimension is of the order of nanometers, which means particle levels or particle sizes should also be smaller or of the order of nanometers. A rule of thumb states that the acceptable particle size must be less than half the first metal layer half pitch. So this sort of gives you the minimum size of the particles that have to be detected and have to be controlled. We can show this by a small schematic. So in the case of a semiconductor, we have seen that there are different levels of metallization. In the case of some of the newer technologies, for example the 32 nanometers or 28 or even 14 nanometers, there are up to 11 layers of metallization. So the first layer of metallization is what we use. So this represents the metal lines. The first layer of metallization is usually the highest density, and as you go up, the density of the metal lines reduces and the size of the individual metal lines will also increase. So, the distance between the center of the metal lines and the metal line itself is your half pitch. So, the size of the particle should be less than half of the half pitch. So, this makes sure that the particles do not cause any shorting in the case of metal lines and ruin the performance of the device. If we have a defect particle here, this is essentially a non-critical defect because it does not cause any shorting. So, these kinds of defects are okay. But a defect that essentially bridges two particles can cause an electrical short. So, this becomes your killer defect. So, not only the defect size matters, but also the location of the defects. So, with reducing feature size or reducing device dimension, the size of the defect or the size of the killer defect will also reduce. Which means we should be able to detect and control these small defects. We have looked at particles. The next type of contaminants is your metal ions. So, why are metal ions bad? The reason being, of course, they are metals. So, they have some sort of an electrical property which can affect the electrical property of the device, because you are essentially building an electronic device, and we saw that the typical dopant concentration is of the order of 10 to the 15 or 10 to the 17 per centimeter cube. This is in the parts per million or parts per billion range. So, any metallic defects with a concentration in the order of parts per million or billion or even higher can affect the electrical properties of the device and once again destroy our entire die. So, metal ions are essentially electrically active impurities Another name for them is a mobile ion contaminant or MIC. So, these usually have a high mobility within the semiconductor. So, they can basically bury deep into the semiconductor and affect the properties. So, a most common form of a mobile ion contaminant is sodium. Sodium is usually present in some of the process chemicals that are used for IC fabrication. So, they essentially have a chemical source, and even a sodium concentration as low as 10 to the 10 atoms per unit area can affect your device and cause its electrical performance to degrade. So, for use in the IC industry, you have to essentially develop low sodium grade chemicals. So, the regular purity of chemicals that are routinely used in other areas is actually not sufficient for the IC industry. So, we specifically need chemicals that have a low concentration of metal ions in order to reduce any contamination due to the metal ions. So, the next classification of contaminants are your process chemicals. So, these are essentially unwanted additions or unwanted chemicals that add on to the regular chemical that you are using. So, these essentially act as impurities to the chemicals that are used in the IC fabrication. So, some of the common areas where chemicals are used are in lithography, where we use photoresist, we also use chemicals for etching. So, etching is to either remove the layer of silicon or to remove any metal layer that is there in your sample. So, in etching, this is typically in wet etching. We also use water, usually some sort of deionized water is used for cleaning. So, in all of these areas, any impurities to the chemicals that are used can again affect the quality of the device and can again degrade the device performance and affect the yield. In the case of chemicals, chlorine is usually the most common contaminant. So, if you are using a chemical for etching, chlorine can essentially affect the etch rate. Bacteria is another type of contaminant. So, this essentially acts as a particulate contaminant because typical bacteria sizes are again of the order of nanometers or more. Bacteria are also the source of metallic ions, something like sodium or potassium. So, they can also act as a mobile ionic contaminant, so MICs. The last type is your airborne molecular contaminant or AMCs. So, as the name implies, these are essentially airborne contaminants. So, the component need not essentially come in contact with the wafer, but through the mini environment, we will see what a mini environment is later on, it can essentially contaminate the wafer. So, these are contaminants that come from, say, the process tool. They could be from the chemical delivery system, so even the simple process of transferring wafers in a fab can cause airborne molecular contaminants. So, wafer transfer in the fab. So, in most commercial fabs, wafers are not transferred by hand. So, because these are essentially 12-inch wafers and they are typically transported in boxes of 25. So, these are transported in special plastic containers called FOUPs. A FOUP stands for a front opening universal pod. So, it is an acronym for a front opening universal pod. So, wafers are essentially stored and transported in these FOUPs, but once again these are plastic containers. So, any outgassing in them can cause airborne contaminants, so which can again affect the wafers. So, if wafers are stored for a long time in these FOUPs, then you will find that there will be some sort of contaminants on the surface. Not all of these will be killer defects or killer contaminants, but some of them have the potential to be killer defects. So, usually some sort of a nitrogen purging is done in order to minimize contamination, but this can cause additional issues with the purity of nitrogen. So, the point is there are different types of contaminants for wafers in the fab, and all of these have to be minimized in order to improve the yield of the wafers. So, what does contamination essentially affect? So, we look at some of the issues of contamination. So, we look at contamination problems, or why is it essentially bad. So, the presence of contaminants in your device can have three major effects. So, the first one is it can affect device yield. This is straightforward. It can basically lead to the failure of the die and an increase in cost. It is accompanied by a lowering of the yield. It can also affect the device performance. So, in this case it leads to a lowering of the performance of the device. This is essentially bad when it happens over a time frame, because it leads to a lowering of the device lifetime. So, this is harder to detect than a device yield, because failure has not occurred, but the device does not perform at its optimum value. So, usually some sort of electrical testing can be done in order to measure device performance. So, this also can be measured and taken into account, but the most pernicious problem due to contamination is when it affects device reliability. So, these are essentially hidden defects which are known only during the service of the device. they are much harder to detect because the device is still works, so yield is not an issue. And the same time any electrical testing will also not show up these kinds of contaminants, but during the service of the device, when the device is in operation, can essentially cause failure. A common example of a defect that causes a device reliability failure is the mobile ionic contaminant, MICs. So these can essentially diffuse into the device over time and can affect the properties. So we have seen the types of contaminants. We have also seen the typical problems that arise due to contaminants. So next we need to look at some of the sources of contaminants and how to eliminate this. So this is one of the reason why work in the fab is all carried out in a clean room in order to minimize the various sources of contamination. So what are some of the general sources of contamination in the fab? The first of course is the fab air or the fab atmosphere. The fabrication facility itself can be a source of contamination. The clean room personnel, so people who work in the clean room would be a source of contamination. The process chemicals and the process gas, even the process water that is used is a source of contamination. So process water, chemicals and gas. Static charge, so this is because most of the surfaces are essentially insulating, where they rub against each other can cause a static charge, which can again affect device performance. Of course, process equipment. So to minimize the contamination due to the first three, which is the fab air or the fab atmosphere, the fabrication facility and the clean room personnel, we essentially go for a clean room for semiconductor manufacturing. So what exactly is a clean room? So a clean room is defined as an area with a controlled amount of contamination or a controlled level of contamination. The operative word here of course is controlled. So this is usually specified by telling the number of particles or number of contaminants per unit volume. So this could be meter cube or feet cube at a specific particle size. So we not only mention the number of particles, but we also specify the size of the particles. So remember, with increase in IC technology, we have smaller and smaller particles because we have smaller and smaller device dimensions. So, we need to have contamination or the defect sizes should be of the order of nanometers. There are different standards. The most common standard is the ISO clean room standard, which mentions the size of the particles. Based upon this, you have different classes of clean rooms. We will talk about class. So, talk about particles per unit volume. So, particles per meter cube, and we also said that we need to specify the size. So, greater than 0.1 micrometers, which is 100 nanometers, and then greater than 1 micrometer. So, you can specify the class of your clean room either using 0.1 micrometer size particles or 1 micrometer size particles. Based upon this, a class 1 clean room can have only 10 particles whose size is greater than 100 nanometers and 0.083 greater than 1 micron. A class 2 can have 100. So, this is essentially a log scale, 0.83. A class 3 can have 1000 or 8.3. A class 4 can have 10,000 or 83, and a class 5 is 10 to the 5. So, smaller the class number, so smaller the class number, better your clean room cleanliness is, because the number of particles is smaller. Of course, to achieve a smaller class number, we need better contamination control. So, different sections of the fab would essentially have different classes. So, the section where the wafers are essentially exposed will have the smallest class number or the highest cleanliness. So, there are different designs for the clean room in order to achieve these different contamination levels. So, there are different designs for the clean room. The earliest design is called a ballroom design. So, in this case, the wafer fabrication was done in chemical hoods, which were separated by clean room filters. So, hoods were used for fabrication, and essentially wafers were transported from one hood when the processing is done to the next hood, and this was typically done by hand because the wafer sizes were also small. So, within the hood, HEPA filters, and HEPA stands for high efficiency particle attenuation. So, HEPA filters were used within the hoods in order to minimize contamination, but usually the device dimensions in this case were of the order of micrometers. So, contaminant sizes were also of the order of micrometers. So, the ballroom design basically gave way to the tunnel and bay concept. So, in the case of the tunnel and bay concept, physically different sections of the fab were physically separated by walls. So, the bay represents the clean areas of the fab, and the tunnel represents the area between the bays. So, within the tunnel were all the areas for doing any sort of maintenance work on the fab equipment, while the wafers themselves were only exposed to the bay. So, this way the wafers were kept clean and contamination was minimized. So, this in turn gave rise to the bay and chase concept. This is again based on the ballroom design. But instead of having a physically separate tunnel and bay where they were essentially walls, the problem with walls is they would occupy space. The fab was virtually divided into a bay and a chase. So, a bay again represents a clean area, while the chase represents the area that is not clean. So, based upon this, we can look at a cross section of the fab. So, we will start from the bottom. So, below the fab is a non-clean area which is called the subfab. So, the subfab usually has all the areas for the process chemicals that are stored, all the cylinders for gas injection or gas supply, all of that is stored in the subfab. There is a raised metal floor on which the fab is housed. So, this is not a solid surface, but usually has some amount of openings. So, within the raised metal floor or above it, you have the clean bay, and then you have the chase that is surrounding the clean bay. Right above the clean bay, you have a provision for flowing air through the fab. And then there is a recirculator for cleaning the air. This is the recirculator. And then outside air is entered into the fab. So, the air essentially flows down through the clean bay area. So, the air goes down and then gets recirculated through the chase. So, the air flows down through the clean bay. So, any contaminants are essentially blown down through the raised metal floor, and then they go back up through the chase and are then taken out through the fab. So, this way, without having a physical wall, it is possible to maintain the cleanliness in the fab. So, by having a bay and a chase concept, it is possible to minimize the contamination due to the air and the fabrication facility. For fabrication facility and clean room personnel, the wafers are not exposed within the fab, they are exposed in a region that is called a mini environment, which is usually an enclosed region which is just before the process equipment. So, wafers are transported through FOOPs, and this is done overhead, and then there are robots which basically grab the FOOPs and then take it into the mini environment where the wafers are opened. So, this way the wafers are not exposed to the fab air or to the clean room personnel, and that way the contamination in the wafers is minimized. Another contamination source that we saw was the process water. It is also related to the process chemicals. So, water is basically used for etching, for cleaning, etc., and typically wafers are rinsed many times. So, a normal water source will have dissolved minerals and impurities. So, for clean room work, deionized water or DI water is used. So, this is water that has been removed of all of dissolved minerals or impurities, and DI water is usually measured by its resistance. So, higher the resistance of the water, purer the value is. Deionized water has a resistivity of 18 mega ohms per centimeter. If you compare that, regular water has a resistivity of 0.004 mega ohms per centimeter. So, deionized water is typically 10 to the 4 or 10 to the 5 times purer. We also have process chemicals, and we said that any contaminants in the chemicals can lead to contamination of the wafer. So, chemicals that are typically used are acids, bases, solvents like acetone or ethanol or IPA, which is isopropyl alcohol. All of these are used. Typical contaminants in them can be metals, can be particles, can even be other chemicals. So, there are essentially established standards for process chemicals. These are called electronic grade. Or semiconductor grade chemicals. So, these are essentially chemicals with 6 nines purity. When we say 6 nines, it is 99 but followed by 6 nines. So, we essentially need high purity chemicals, not only chemicals but also gases, in order to make sure that there are no contamination due to the process chemicals. Not only the chemicals must be pure, but the chemical delivery system must also be pure. So, usually there is some sort of a bulk chemical delivery system called a BCD that is set up in order to make sure that the chemicals that are delivered to the various process equipments are all pure. So, we also have to look at cleaning of the wafer surface, because these can also be a source of contamination. So, clean wafers are essentially needed for each and every step. So, the wafer surface has to be cleaned at every step. This again makes sure that the contaminants to the surface are essentially minimum. So, some of the types of contaminations can be particles, organic residues. These essentially come from the chemicals that are used. You can also have inorganic residues, and unwanted oxide layers. So, typically these are silicon dioxide layers. So, we have different cleaning strategies depending upon whether the wafer is located in the front end of the line, FEOL, which is your front end, and you also have the back end of the line. So, we have different cleaning strategies for these different areas. So, in the front end, the cleaning should not affect the surface roughness. The front end of the line is where the various elements like transistors and diodes are defined, so that the cleaning should not affect the electrical characteristics of this. In the back end, this is where the electrical and the metal lines are formed. So, electrical shorting is the major concern. So, wafer cleaning essentially involves some sort of particle removal, usually by blowing air, and then chemically cleaning the surface with a mixture of acids, usually sulfuric acid and hydrogen peroxide is used. This is to remove any unwanted oxides. Sometimes HF is also used, and then the wafers are again cleaned with DI water and then blow dried in order to remove any particles in other contamination. So, usually after some sort of chemical processes like say lithography or etching, usually a cleaning operation is performed in order to remove the contaminants and make sure that the wafer is clean before it goes on to the next step. So, today we have looked at the various ways we can maintain the cleanliness in the fab. So, one way this is achieved is by choosing the appropriate fab design, but it is also done by making sure that we have clean process chemicals, clean gases, clean DI water, and also by periodically cleaning the wafers during the fabrication process. So, in the next class we are going to look at the various components of your integrated circuit. So, we saw that the integrated circuit is essentially formed from various devices like diodes and transistors. So, we are going to see how all of these are fabricated and how they come together to form the IC circuit.